Okay, everyone. Welcome to our Tuesday lecture. Right. So today we're just going to work more on Unit 7. So Unit 7, working with heterogeneous data sets and a view towards machine learning. Heterogeneous data sets means data with different types. So we were looking yesterday at tables and relations and things with strings and numbers and dates and different types of data in one data set. What we're going to do now for the remainder of the unit is to head towards machine learning. So I'm going to give an introduction to machine learning, unsupervised learning, supervised learning today. And on Monday next week, we are going to cover the specific techniques we're going to use in project 3, which is tree-based techniques, decision trees, and random forest techniques. But yeah, let's just start with a quick recap of what we've done yesterday, because it's good just to see. Data is often stored in databases, usually in relational databases. We covered off what relations are, how in an industrial system data might be stored for a system such as LinkedIn, what SQL is, which generally is a language you'll use to create CSV files and things and pass them around to each other. And then with such a CSV file, you'll load it into a language like Julia or Python or R or your favorite language, and be able to manipulate it and explore the data. Okay, so we went through an example of looking at athlete data from the Olympic Games. We had a 40 megabyte data set, and we did a whole bunch of analysis on it, sort of culminating in the fact that we could sort of observe athletes getting a bit taller over time, but only if we slice the data up correctly because of confounding factors. So if we looked at the total data set, the height of athletes was fixed. But when we diced it up into cohorts, we could see that actually over the last 100 years, people have indeed grown 5 centimeters taller, or at least athletes competing in the Olympic Games have trended to be a bit taller. Yeah. So, and we briefly spoke at the end about how to handle larger data that wouldn't fit on one computer, or at least in your RAM. But yeah, we're going to move on from here. We're going to go into machine learning, which is a fascinating topic. So generally, what has been realized over the last 20 years is now that we can collect large amounts of data and curate it and keep it in databases and have access to all these things, you can actually get a lot of insights out of it. Sometimes insights are quite obvious, and you don't need much data, and these are the kinds of things, the kind of analysis people could do before computers, for example, or at least in the 1980s or something. But sometimes data only contains weak trends or weak correlations where you might need a million data points to realize, or to high statistical accuracy that maybe you could split the data into 2 groups or something like that, or like two variables that are sort of related to each other in some way. And so how do you go about looking at how things relate to each other in data? How do you extract insights from data when the data is many millions of megabytes or something like this? Yeah, so machine learning is just a fancy word for getting a machine to sort of tell you to extract insights from data, essentially. It's sort of the way I think about it. Yeah, so the kind of data sets that you use for machine learning, they tend to be a little bit large. There's also, a very large blossoming research field around machine learning, okay? And one thing researchers like to do is they like to create an algorithm and compare it to other people's algorithm. And to do that, they need a kind of level playing field, right? So what they've got out there is a series of very famous example data sets, okay? So we're going to look at one here called MNIST digits data set. So if I click on it. This is one which is a database containing a series of digits, handwritten digits. Okay, so like, for example, the US Postal Service wanted to automate aspects of their mail delivery system. So one thing they could do is look at the zip code and get a computer to figure out what the zip code is, and then put, shuffle the envelopes into the correct bucket so that a human doesn't have to do it. So it's sort of like a time and cost saving measure. And also an accuracy measure in sometimes as well. So, with a system like this, with this optical character recognition, many things in the 80s and 90s and 2000s managed to get automated through computers and robotics and things like this. And with systems like this, you may even do things you wouldn't have even bothered to do with before computers. In the 80s we had post, but what we have now is, Google, digitizing, the entire history's worth of books, because they can just, Google's got plenty of hard disk space. They can store the images, and they can do character recognition. So it's pretty easy to take an old book from 1,000 years ago, pass it through a system that does character recognition, and create a kind of digital copy of the book that you can search in Google and see Google ads. So there's always an angle. Okay, so MNIST is probably just perhaps the most famous, or one of the most famous of such data sets. There's other ones. There's ones about flowers, the Sshaped data set, Iris Sshaped data set, and then numerous other training and data sets that people use, so that they can take algorithm A and algorithm B and see what they do to the same data and say, haha, my algorithm's better. Okay. So the other reason to have a data set like this is sometimes your models can generalize. So, well, like for example, for the case of digits, you don't have to be doing post, you could read digits anywhere. But in a lot of the image recognition things, you could apply the same sort of models to look at images. You could load the model onto your the software that runs your phone camera to do detection of what's in the scene, or Facebook could use the same algorithm. Different people could just take things, train them on open source data sets, and put them in products in the end, or in software in the end. So in Julia, there's this package called ML datasets. So you can, oh, there's lots of enters here. We can go like using ML datasets. Inside it is a bunch of famous kind of examples. The Iris one there I mentioned. I'll just mention Boston housing here for a moment, because we're going to do a housing example in Unit 3, Project 3. So this is a famous data set where you have all these features relating to houses and a lot of sales prices for houses. And you want to use machine learning to predict, given that the house has 3 bedrooms and is 10 kilometers from the city and has 2 garages and 1 bathroom, how many thousands of dollars do you think it's going to sell for? Okay, so real estate is a big industry. It has a lot of money flowing through it, and being able to do this stuff sort of accurately is very profitable for the people who can do it more accurately than other people. So there's sort of been an outrageous amount of effort applied to these kind of problems. And also there's a kind of outrageous kind of guarding of data sets, because you can make real money out of models trained on such data sets. So often you have to like pay for access to the raw data and things like this. But the Boston data set's a free one, and the Melbourne one we're going to use is also free. So the MNIST example here, there's 2 sets of data, what we call the training set and the test set. So if you want to know how well an algorithm does, well, you're going to need something to test it on. Okay, so the 10,000 test set characters are sort of like, a human's gone through and marked each digit as 0 or 2 or 5 or whatever, And it's sort of like the truth, quote unquote truth. And you can run an algorithm on it and compare it to the truth, the golden truth, or whatever you want to call it, and give a percentage accuracy. You know, you might be 98% accurate or 99.5% accurate or something like this. The other 60,000 here are the things you can use for training. So if we're going to deal with supervised learning, so the idea is you have 60,000 other digits where you've marked which one's 5 and which one's 9 and so on, and you can use it to train an algorithm. Okay, so you could go in and hand code an algorithm and teach the computer that a 1 looks like a straight line and a 0 looks like a circle, and sort of hand code a computer program to do that for you. In machine learning, you're not necessarily doing that. You're giving it examples of things that you find in the real world, and it just figures it out on its own. Okay, so that's what this training set is about. It's the set of examples it can use to try and figure it out. So we can use this ML datasets thing to fetch things from the internet easily. Basically, that's what all it's for. And it puts it in a nice format like arrays and things for you and Julia. You know, we can look at the labels and the test. So we have labels that's sort of like, the labels here is the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the data are the actual images. So generally, you could think of an image in something like Julia. It might be like a matrix of intensities. So you could think of this as a negative of, like, if you're drawing on white paper with a pencil or a black pen, this is kind of a negative of that kind of image. So if we just look at the first 12 digits from this and we print them to the screen, this is what it looks like. So there's, it's a pixelated image. They're kind of low resolution. We've got this written down here somewhere. The images are 28 pixels by 28 pixels. So there's 784 pixels per image. Okay. And to a computer, we've taught the computer how to draw a 28 by 28 image on the screen in the web browser, but that's because the web browser has a computer program that knows how to interpret images and things. To a computer or to a machine learning algorithm, it doesn't necessarily think of it as a two-dimensional image. It's just a bunch of 784 pixels. And some algorithms will know about which pixels neighbors to which other pixel and things like that, but some of the simpler algorithms won't even care, about locality and things like that. So you can just give the computer, well, we have 784 data points. Can you please predict whether that's a 2? Okay, that's the kind of thing we're going to do with machine learning. Okay, and we have 60,000 of them. Okay, so we have 60,000 different digits here. Each of them with 784 pixels. So if we flatten out this image, that's like, scan line, scan line, scan line, scan line, scan line, scan line, and put them all in a row, that's going to be a row of this matrix, okay? And then there's going to be 60,000 rows stacked on top of each other. Okay, so I've just gone through here and we've plotted in a heat map, which is like a thing from plots.jl, which lets you do 2D plots. These things, matrices flattened into vectors in terms of scan lines, and then all 60,000 vectors stacked on top of each other. Okay, and what we can see here is there's some banding. Okay, so there's black bits in between. That's because no one tends to write near the left edge or the right edge of the image. Okay, and similarly, not really at the top or the bottom. So there's a lot of black on the left and the right, and there's a lot of black in between the scan lines. But otherwise, it just looks like a sort of jumble. Okay. Now, one thing I alluded to last lecture was saying that if you can sort your data, it's kind of like it's a super trick. Okay. If we want to think about grouping data, you could group data into dictionaries of different things. But if you just sort it by some grouping key, the things within the same group just are next to each other, and then there's things in the following group that are next to each other. So down here, we've just sorted these things such that they're sorted. So this is sort perm returns a permutation such that would sort the labels. Okay. And what you can see is now this image is kind of banded into digits. The bottom band here is 0, and then 1, and then 2, 3, 4, 5, 6, 7, 8, and 9. Okay. And you can kind of see with your eye here, even though these images have sort of been flattened out into lines, into pended scan lines, you can still see with your eye, certain patterns or whatever in each band. Okay, and so it's kind of believable that you could train a computer program, or you could write a computer program to figure out which band is which, and you could give an example which band does it belong to. Okay, and that's what we're going to do with machine learning. Is we're going to give all these examples here, and try and figure out a few different things. With the unsupervised learning approach, you might try to determine that there is in fact 10 digits here. With the supervised learning approach, you're trying to create or train a new model or create a new algorithm, which can determine, given another example, is that digit a 3 or a 9 or what is it? Something kind of quote unquote useful. All right. We have a question from Joshua. If we wanted to ask assignment questions, is there time for that today, or consultation session only? Let's see how long this lecture takes. I'm happy to take questions at the end if we finish it a little early. There is a consultation hour tomorrow 5 with Yoni, and I think 5 to 6 with Yoni PM, and tomorrow 7:30 to 8:30 PM with me, I believe. Use the same Zoom link. Okay, unsupervised learning. Okay, so supervised versus unsupervised really has to do with the fact in advance, do we actually know what the digit was or not? So this training set had images and labels, right? So here, we have the labels here, and here's the images. So if we deleted the labels and we only had the images, we still have data, okay? We still got lots of interesting data. And if you look at this picture here, you can kind of probably believe me that the data fits into 10 different categories, okay? So without knowing what the labels are, can you get the computer to, for example, cluster all the handwritten digits into categories of its own making? It doesn't have any semantics about what a 3 means, but can it sort of figure out, oh, there's a bunch of images, they all look similar, we're going to put them in a bucket. To a human, they all look like 3s. And can it take all the images of 2s and put them in another bucket? To a human, it all looks like 2s. Can we get it to do something like that? So, yeah, if you think the labels are represented by capital Y here, and the data or the images or the features that you get as inputs are represented by capital X. In unsupervised learning, you're not worrying about Y, you're just dealing with X, and you're trying to figure out interesting things about the data just knowing X, okay? So one way of sort of dealing with data, we saw an image which had 784 pixels. And really, given the fact that there's only 10 digit, a vector space with 784 components is probably a little bit of overkill to describe our data, okay? It could probably fit into a smaller dimensional space, so to speak. And so principal component analysis is a technique you can use to automatically project your very large input vector space. In our case, that's 784 pixels, each with an intensity. Okay, so it's like a vector with 784 real numbers in it. Can we just reduce that down to a smaller dimensional vector space and have a look at that? So such projections, they might be linear projections, linear functions from linear algebra, or they could be more complicated nonlinear things, okay? So complicated nonlinear things are fine and very interesting, and certainly that's studied a lot in neural networks. Neural networks, we aren't going to be able to cover a lot about neural networks in a few hours of lectures, but UQ does offer courses on machine learning, and they're fascinating, and you can definitely pick that up in 3rd year, I believe. we're just going to look at a linear technique here, where we're literally taking vector, like a large vector space, and projecting it to low dimensional vector space. So if you're not heavily into linear algebra and stuff, think about our three-dimensional world and projecting an image onto a two-dimensional plane. So like taking a photograph, or like me on this camera here. So we're going to take our 784 dimensional space and squash it down onto just 2 dimensions. Okay. Now, why would we want to do that? Well, it's actually really interesting because a human can, as a part of data exploration, can look at the data in these 2 dimensions and see if we can see any patterns. Okay. So here's some Julia algorithm stuff. It's actually quite straightforward to implement something like PCA, but this isn't a linear algebra course. I don't want to really get into singular value decompositions and various things like that. So here's an example of it written out using a library called multivariate stats, which is a stats library, and it just has this magic PCA thing. So this thing is a bunch of code I'm not really going to explain, but what it's really doing is it's going to create a matrix, M. The matrix here is 784 dimensions by 2, okay? So it contains the 2 most important basis vectors as far as the algorithm has detected, okay? So how do you find those 2 basis vectors? Well, one way you could do it is with the singular value decomposition and look for the 2 biggest singular values. But yeah, so that would be a singular value decomposition on this matrix or this matrix, okay? And those basis vectors, they don't care what order you've ordered it, so the ordering is kind of irrelevant. So M is a matrix. It's a 2 by 784 matrix, so it contains 2 basis vectors. And what we can do, and that 2 is chosen here, right? Okay, so we've told it to find 2. We could tell it to find 10 basis vectors. Maybe we could find all 10 digits, potentially. So let's see. Those basis vectors themselves aren't going to be the actual representative of the digits. They're just the vectors which sort of describe or distinguish the various examples maximally in a way. So you can kind of think of it as if you have a blob, it's looking for like the first vector is like the direction with the greatest variance in a way. All right. So then in here we've got this function compare digits. So we're going to look at like digit 0 versus digit 1. So we're not going to have all 10 families of digits on the one plot. We're just going to plot 2 of them at a time, just to give you a flavor of what's happening here. So imagine we only had examples of 0s and 1s. Right, so we've created this M just from the data. So this is coming just from X, which is the images without the labels. And we're going to filter our X's down to just, so what this is doing is looking for all the labels, which is equal to DA. So for example, in this first plot here, we're looking at digits 0 and 1. So it's going to look for all the labels equals 0 and get the indices of those and project the X down into a smaller matrix. So essentially XA in that first plot is this first band of stuff here, and XB in the first plot is that second band here. Okay. They're still quite large matrices with, thousands of elements, but rows. And then we perform the projection. So if you have a isometric matrix M, which is like an orthogonal or a unitary matrix but trimmed, then you can use it to create a projection. So we're just going to project basically our X into the space defined by M, the subspace defined by M, and do a scatter plot. Okay, so we've projected our 784 pixels down to 2 dimensions. And if we have a look at, say, 0 and 1 on the scatter plot, you can kind of see something really interesting here. You can kind of see that the 1s have always ended up on the left here with a component in this direction of about 0. And the 0s are ended up more on the right with a large amount of this component. There's also a little bit of a slight difference in how component 2 is coming out between these two data sets. And you could imagine trying to visualize this in 3D. You'd have 3 basis vectors and visualize a point cloud in 3D and kind of look at it. But what we can see in this case is just the first basis vector can distinguish 0 and 1 quite strongly. You could put a cutoff here at 2.5 and say everything to the left is a 0, is a 1, and everything to the right is a 0. Okay. On the other hand, these 2 basis vectors, they're not so great at distinguishing digit 2 from digit 3. Okay. And then you can sort of see different smear patterns with different digits. Now, like I said, this is, if we're doing unsupervised learning, how is this helpful? So you're a human, you're sitting in front of the data, you do some PCA and you plot some stuff. And let's say our examples were all the 0s or 1s. There was no 2s and 3s and so on. You're gonna plot this thing and you're gonna see this plot here, except for it's only one color, it's all black, right? But still with your eyes, you can see, oh, there's this blob on the left and this blob on the right, okay? So you can kind of use this approach. You can kind of see that actually, no, this is like a bimodal distribution where there's 2 families or there's 3 families or something like that. And so with your, complete entire machine learning algorithm or, application that you want to build, this might just be, this projection into some space might just be the first step of a multi-step process to distinguish what blob is which, or given an example, which blob does it belong to? Right. So generally, like I was saying, if we did this in 3D, it might be that the blue blob is separated vertically from the red blob, and they would still be distinguishable, something like that here. The more dimensions you have, the more angles you can look at the data, and the more chance you have of sort of discriminating, data set A from data set B. Yeah, but it can be a lot cheaper to do this in a smaller dimension. It can be a lot easier to visualize for a human as well. So then, like I alluded to here, is we kind of ended up with 2 blobs or clusters of data. So another really important part of unsupervised learning, and I would say like the bulk of unsupervised learning is all about clustering, identifying common things. So this could come up in any number of fields. Like we're talking about digits here, but you could have a bunch of medical data about diseases, and then you might run an algorithm like that and then realize there's actually 2 families of disease that we used to be calling the same thing. And those 2 families, just identifying those 2 families might be really helpful, because you might have identified some treatment which was 50% effective, and that might be just because it worked on one of the families, not the other, okay? And so once you can learn to sort of distinguish the 2, then that's a real practical thing, because it helps you diagnose and treat a patient. Okay, so there's, yeah. So one of the easiest ways to think about clustering blobs is to try and find the centroid of each blob. So you could imagine here on this top left, you can imagine there's some centroid of this blob there and some centroid of this blob there. And that could sort of be descriptive of each blob, okay? The other way you can kind of do it is you could imagine finding some line or some surface separating the 2, so that you can kind of say, oh, the left of this surface is blue and the right of the surface is red. Yeah, but we're not really going to cover either of these in depth, but I just wanted to show you something called Kmeans. So in Kmeans, K stands for the number of clusters. K is just, it's sort of like our MM1K models. The K is just a math term for a number, integer. And you're trying to find these centroids or means. So in the K-means thing, the goal is to come up with, start with some data here where everything is unlabeled, and then to sort of automatically group them into little subgroups. So you look at this data, maybe a computer or a human just guesses that there's 3 things in there. So you set K to 3, and then you set the algorithm loose. And what this algorithm does, it'll try and find 3 centroids here in an iterative way. So it'll put 3 centroids out in space in random places. It will then grab all the points. Every point will be assigned to its closest centroid. Okay, if you're closer to, if you're this point here, you're closer to the centroid of the blue blob than the black or green blob. Okay, so you just get colored blue. Then now you've assigned, you started at some random place. So you're going to have some red, black, and green points. Then you're going to segregate the data, and then you recalculate the centroids based on the data sets themselves. So you get all the blue things and you find the mean, the centroid of that blob, and you move that there. And you do that for all the categories, and you repeat and repeat and repeat until it converges. It'll eventually converge to something where it's split the blob into blobs. And it's a really simplistic but sometimes effective method, and you can do more effective and more complicated versions of the same thing. Yeah. So let's do that here, where we actually take this 784 dimensional space, and we're looking at 10 centroids in a high dimensional vector space. If we do that and we run the Kmeans algorithm on it, we end up with this. Okay, so it's actually managed to identify, like this is the centroids themselves. Okay, it's managed to identify a number of digits essentially, but not all of them. It's quite clearly got a 1 and a 3, 2 and 6 seem pretty separate. 8 seems pretty separate, but it's a bit confused between 4 and 7 and 9. They're all kind of like superpositions of each other. Okay, so this is sort of like just some really, really simplistic, stupid linear method in a high dimensional space. So it's managed to sort of mix together the components of those, but roughly speaking, it hasn't done too badly. It has done something somewhat useful. Okay, so this is, you can imagine an alien species coming across a bunch of handwriting and running an algorithm like that to figure out what our digits are or something like that, without having any idea. But obviously there are more advanced algorithms that are more effective at separating 4s and 7s and 9s and stuff like that. So that's all I want to say about supervised learning. Unsupervised learning, sorry. Supervised learning is probably slightly larger field of machine learning. It's really exploded over the last decades because a lot of the techniques, there are some techniques that have come out in the last 15 years, 10 or 15 years, or 5 years, some of them, which have really been pushing the envelope, pushing the state of the art forward quite a lot. Okay, so things that your camera does these days in terms of like focusing on people's faces even, or more advanced things in terms of image correction and stuff in the camera. There just weren't algorithms that were feasible 10 years ago. Never mind the fact that the hardware was slower, the algorithms really were kind of shit, like 20 years ago, let's say. Face detection worked 10 years ago, well. But yeah, so we are only going to give you a taste of this. But so the largest probably category of new sort of techniques is this deep learning. Okay, I'll explain what deep means in a minute. But it's certainly, yeah, really pushed the envelope forward. So there are different kinds of problems you want to solve with supervised learning. There might be like 2 examples. For example, is I've got some data about houses, and I want to predict the price of the house. Okay, so I know how many bedrooms there are, the distance to the city, the number of windows, number of cats. I'm not sure if that's relevant. And you want to regress a number. Okay, so you've probably heard the term linear regression, which was where you like can fit a straight line to some data, and then read off that straight line at a given x. You can read the y. Okay, so you can predict a number. And then there's another kind of problem called a classification problem, where it's not like, you don't want to predict a number, you want to predict a class, or it might be, it could be true or false. That's a simple classification problem. Like, is this a hot dog? Is this image a hot dog? So there's a, you know, you can make a classifier, which is hot dog, no hot dog kind of thing. In our case, the case we've been studying here is you know, we want to classify each image as being a 0, a 1, a 2, a 3, a 4, a 5, 6, 7, or 8, or 9. Okay. In practice, with those kind of classification problems, we might do something like that is called one-hot encoding kind of the problem. Or you know, what we might do is we might train a true-false classifier for 0, and a true-false classifier for 1, and a true-false classifier for 2. And we'd train 10 classifiers. We'd run all 10 classifiers over the image, and we'd assign the label as the classifier that thinks it's most 2-ish. You know, the classifier that's 2 might say I'm 80% confident this is a 2, and the classifier which is 3 might say I'm 40% confident it's a 3. So you'd pick the most sort of likely or the most confident answer. Yeah. So before we go on to some algorithms that we can actually implement ourselves, I should probably explain a little bit about what is deep learning. So I mentioned before when we did this PCA, when we did all this Kmeans and all this stuff, we're in this sort of linear space, and we're doing these linear operations to transform, you know, this input vector into, say, an out. Maybe you want to go from this 784 pixel input vector to a 10 element set of probabilities. Is it 0? Is it 1? Is it 2? Is it 3? And you could imagine trying to do that with a simple linear transformation, but generally that won't work. You need a more powerful general function than a linear function to do this well. Okay. But we don't really have a language for describing arbitrary functions. You know, the function or the size of possible functions from, you know, dimension 784 to dimension 10 is something ridiculous. I think it's 784 to the power 10 or 10 to the power 784. It's a very, very large number. You can't like just write down all the parameters that might make up such a function and fill it in. So deep learning is actually a trick which actually lets you do this in a way. So we parameterize, what we do is we say our function from input space to output space is going to be a set of simple steps. These conv steps, conv33, that means basically take you know, a 3x3 grid of pixels and do some linear transformation within that 3x3 set of pixels. It's a convolution. You're kind of doing this centered on every pixel. So it's sort of like you're looking at a pixel and its neighbors, and you're making some statement about the pixel and its neighbors. And you do this, say, twice. You know, maybe you're starting from 3 various intensities, and you end up with 64. Oh, sorry. I don't know what that 3 actually means. Sorry, I'll try to stop explaining this in too much detail. And then there's these nonlinear things. So, for example, in a 2x2 matrix, we might take the maximum element. Okay, so we might, and then we've actually halved the dimensions of our picture, because this is also a projection. So it's a nonlinear projection. Okay. And then you do more convolutions, more max pools, more projection, more max pools. And then these are dense matrices, multiplications followed by, you know, some various things. It's not particularly important what they are, but you're basically doing these series of steps. Each step is simple. Well, it's relatively simple. It's something we could program together here. But, you know, to write the whole thing out would take too long. But we could certainly do one of these steps. It wouldn't be very hard. And they're generally nonlinear. So when I mentioned there's this convolution, after you do this linear convolution, which is, you know, basically matrix multiplication, you do this nonlinear thing, ReLU. So you can imagine something like in physics, you might have a diode, which lets through positive current and blocks negative current. So you can imagine the function half x plus absolute value of x. So it's trending up. It's like 1 in the positive x field, and it's otherwise 0 on the right. And so functions like that, that's an example of ReLU. There's also, you know, you have a lot of sort of S-shaped functions, where you know, so it's where a function softly goes between 0 and 1, and you'd apply these kind of things. So you basically element-wise apply nonlinear functions, and then more globally apply linear operations, and then something non-local but nonlinear, and then something global but linear, and you sort of basically do a bit of one and a bit of the other. This particular model came out in 2014. It was pretty good at the time. It was a step forward. Just a year or two later, some much better models have come out that, you know, were sort of deeper. They had more of this concept of joining things together from lower, so there'd be skip connections. They wouldn't just feed into one another linearly. They would also feed into each other like a chain, sorry, but it would be kind of like you'd be able to look at data from earlier steps and things. But at the end of the day, what you get at the end of the day here is softmax. So you're basically getting a number between 0 and 1 or something, which might be like a probability or a certainty of something. And so what you do is there's a bunch of free parameters in here, because these are just matrices, and you run an optimization problem to fit these matrices to the input data sets, so the X's and Y's, such that, so you want to maximize the accuracy of the algorithm. And we won't really cover that, but here's an example of this sort of working. So here's an apple. It's a red apple. But if I were to ask you to classify what type of red apple with this, you probably wouldn't say it's a Granny Smith. But however, keep in mind, this classifier has been trained on everything: dogs, cats, hot dogs, everything. And it has correctly guessed that it's an apple, but it hasn't been perfect. So certainly larger, more complex classifiers would not call this a Granny Smith apple. But this is something you can easily download models and examples into Julia and run. Okay. Here's another data set, the ImageNet data set, which sort of basically has a bunch of strings and a bunch of images. A string describing the thing like apple or something. Okay. So that's a very complex, deep model, but a more simple one is a linear model. So it's basically, like I said before, you want to project from, say, an m-dimensional space to an n-dimensional space through a matrix, right? Or even a series of, well, it's sort of linear problems, so it's sort of equivalent. You could do it per class, so multi-class classification, where we want to have 10 different classifiers. So the way you kind of do this is you apply a linear transformation to the inputs. Potentially there's some offsets, okay? So after the step in a neural network, you apply some local nonlinear thing after that step, but we're not going to do that. So this is going to be, this is sort of an ansatz or like a variational kind of solution. This is what we think Y is going to be, okay? Y is being a number between 0, like 0 if it's incorrect or false, and 1 if it's true, okay? Now, so what we're going to have is a bunch of X vectors and a bunch of, and each one has a label 0 or 1, okay? So this is like, is it a 3? And you have all the examples, and for the 3s, the Y is 1, and for the X's, it's 0. And we're going to say, let's suppose that we can predict this value Y, which is 0, 1, via a formula like this. And then we can say, given that we have all these betas, we can say, how wrong is it? Given all our examples, all our known examples, I, and all the betas, we can calculate how wrong we are. So this is some simple, you know, sort of Pythagorean distance in the psi-dimensional space of how far we are from where we should be. And we can, it's called the loss function, or it could be the cost function or the error function. And it's something we want to optimize. We want to minimize our loss. We want to make sure that our Y's are as close to the Y's as they should be, given our predictions. So all these training, whenever I say machine learning training, what I really mean is optimize the numbers. It's an optimization. Training means optimization, essentially. Okay. It's really fascinating to read the literature because the machine learning people have rediscovered all the optimization techniques well, they've added new ones, plenty of new ones, don't get me wrong, but they've rediscovered and renamed a lot of pre-existing optimization techniques. So it's sort of like a lot of techniques I was familiar from, learning in the early 2000s. Sort of papers came out after that saying, "Hey, I invented this thing and it's called blah." And it's like, I don't know if you invented it. So if it's an optimization problem, one way to solve an optimization problem is linear gradient descent. So you take the derivative of the loss function and you say, okay, let's say we want to minimize loss, minimize our error. You go downhill. So if you think the gradient points uphill, so you head in the direction minus the gradient. And so we can do this because this is now a matrix linear algebra problem. It's very easy to differentiate the loss. And I'm going to skip through the linear algebra here, but you can solve these kind of equations through using the pseudo-inverse and things. So the pseudo-inverse is if a matrix is invertible, the pseudo-inverse is its inverse. But if a matrix is not invertible, the pseudo-inverse is the matrix such that when you apply it, like a matrix might have sort of an invertible subspace. So in that subspace, it will invert things correctly. And for things outside that subspace, it'll sort of minimize the result. Okay, so it's a funny thing, but it's kind of cool. But basically, you can solve this minimization problem exactly through use of the pseudo-inverse here, and then apply that to all of our training examples. Okay, and write a classifier. So what we're going to do is for each of the labels 0 to 9, we're going to calculate our bets. So this is our y's essentially. And then to that, we're going to take it a step further and find the one with the most probability at the end of the day. Okay, so we're not going to have time to cover cover it properly. But we can see we have all these different predictions, and we want to now answer the question, how well did we do? So given we have a set of predictions, so let's say we had we found that pseudo-inverse A with the test set, the 60,000. Now, it's not fair to run your analysis on your training set, sorry, the training set of 60,000. You want to look at some uncorrelated data because your model can easily pick up things it's seen before. You want to really test how well it works on new data. So we've got 10,000 new images in the test set, and we're going to run predictions on those and figure out how wrong it is. So we could just figure out like a rough number, and we're going to get that it's something like 86% accurate. I'm not sure if that's written here somewhere. Oh yeah, here we go. So generally the accuracy is just the number of things we got correct divided by the total number of things in the test set. The confusion matrix is a really important thing. It's telling you, suppose it was a 3 and we thought it was a 4, okay? So that element in this matrix would be here. Okay, you look at like the 3rd row or the 4th column. So the diagonal here is, suppose we thought it was a 5 and it was a 5. Well, there were 659 cases out of the 10,000 things the test set where that happened, okay? And it's called a confusion matrix. What we can see is if we look at this top right corner, the algorithm's been pretty good at differentiating zeros and ones. It's never confused a 0 with a 1 because none of the zeros were ones and none of the ones were zeros, were marked as 0. Okay, which is good because ones and zeros are quite distinctive. But if you take something like 2s or 3s or whatever. So like some of these off diagonal terms are a bit larger. There's 80, so that's 9 and 4. 9 and 4 apparently. Yeah, I guess they could be in handwriting, kind of similar. Yeah, we are slowly running out of time. So generally, the way when you do these kind of deep learning, is you will need to perform this optimization, and you'll probably use a gradient-based method to perform that optimization, gradient-based learning. And this isn't an optimization course, but I probably unfortunately don't have time to do this part justice. This isn't an optimization course, but you can kind of implement various ways of doing this optimization, which is what Yoni has done here, and then sort of plotted the results. So in this case, it's he's plotting. He's got a simpler case. It's a one-dimensional kind of problem, and he's plotting here what the gradient descent algorithm is doing over time, and you can kind of see that in this sort of linear fitting example. So it's beta naught plus beta 1 times x, y equals beta naught plus beta 1 times x. So it's a linear function. That here's the actual exact solution and the solution that the descent minimizer found are pretty much the same. But yeah, optimization itself is a really fascinating topic. Yeah, we won't really be going into that in detail here. So that's just sort of an overview of various machine learning methods. There's another category of tree-based methods, which we will cover in detail on Monday. So in this, we will really be going into the code and the algorithm and how it works, and make some predictions and things. And in your project 3, you'll be invited to create your own random forest classifier. So you'll start with a data set, like a CSV file kind of thing. You'll have to load it with data frames. You're going to have to, you noticed we had to transform our images into matrices. So you're going to have to transform your data frame into a set of matrix X and vector Y, and then apply your tree-based model to that. Okay, so we'll go through that in detail on Monday, which I look forward to. Now it's 6:52, so I rushed through that because I know some people might want to ask some questions. So first, I'd like to invite questions about machine learning. Has anyone got any machine learning focused questions they'd like to ask about the content today? I'll give everyone home a moment. Okay. Then would anyone in the room or at home like to ask any questions as a group that might be pertinent for project 2 before we head off? Yes. Keep in mind, we also have the consultation hour if you want to keep it private, but there's no such thing as a stupid question. So please shoot, Alexander and Joshua. Yeah.
Okay, does this work? Can I speak on the...
I can hear you, sorry.
This is general question. Are we marked on the efficiency of our code in terms of runtime? Because it seems to me if you're running a code for like 10 to the 7 seconds, you're going to be encountering a lot of your code is just going to take a while to run. Yes. But also for specific parts, namely for scenario 4, because you have an infinite buffer, the code seems to be really slow no matter what I do to optimize it.
Oh, okay.
So how much are we marked on speed of code, if that makes any sense?
Yeah, it's probably most safe to direct these kind of questions to Yoni, as the course coordinator who's in control of all the marking schema. But I think be pragmatic about this, right? Like I don't know if you're going to get a different grade because it takes 2 seconds instead of 3 seconds. If you can make the computer give you the results before Friday and you could hand in their results, I imagine that's sufficient. there was 20% of the grade marked to elegance and efficiency of your code, 60% for correctness and 20% for the perspective seminars. So perhaps it will factor in.
Just to clarify, I know you're not uni, but it was also said that like the 20% was also for like, you know, good coding. Does that also include stuff like breaking the code into like different files and not having one big file and commenting correctly? Does it include that stuff as well?
I imagine it does, yes.
Okay, good. So I haven't wasted all my time breaking all that stuff up. That's good to know. All right, thank you.
Good practice regardless. Yes. We have a question in the room. Yeah. Yes. Yeah. So the question is, you know, with the long 10 to the 7 time simulations, is it really feasible to capture all the sojourn times in a vector? I would say most computers, you're not going to run out of RAM, but I might be wrong. Certain lambdas could be wrong. And the other part of the question was, you know, could you do it incrementally? And yes, there's this whole field called online statistics. So an online algorithm is an algorithm where it's like your Google on the internet and people throwing data at you, and you can't possibly store every piece of data on your disk and look at it later. You kind of have to process it, forget it, delete it, right? So for something like a mean, there's an online algorithm where you like someone sends you a stream of data, you know, after you get one element, the mean is just that element. You know, when you get 2 elements, you divide it by 2 and add half of the next example. And then you could take, with the 3rd element, you could take 2/3 of what you just had and add 1/3 of the new one, and then 1/4 and 1/5 and 1/6 and so on. So there's an online algorithm for finding the mean. There's no exact algorithm for finding the median in an online way. There are approximations that work really, really well in practice, but there's no exact way because it really actually depends on the details of the PDF. So yeah, it's a great question. Probably best to figure out through trial and error. You know, you'll see an out of memory error if it's a problem, but yeah. We have a bit of text on the screen here, Joshua. For the 3rd plot, the one about the distribution and the time, yes, I've managed to get an array of times for each of the people, people in the system, although I'm not sure they're correct. But I'm not sure we'll do it now. Is it a histogram? Is that what we want? Okay. So we want you to demonstrate some, the empirical distribution. One way of demonstrating that is with a histogram. Some people would much prefer to use to plot a cumulative distribution function. Okay, so you can take that vector and you can create histograms. You can create CDFs and things out of it. There's tools in like plots.jl has a histogram function. There's statistics, stats-based statistics, probably a couple other packages like that, which would help you, for example, bin things into histogram. Or if you want to do it manually, it's not so difficult to actually bin things to histogram. If you know in advance your bin size, your min bin and max bin, it's actually pretty easy to write a loop to do the binning. Or again, you could do the same with a CDF, binned or not binned, either way. So the easiest way to do an unbinned CDF is just to sort the data and then linearly interpolate between 0 and 1 on the y-axis and just plot that, and that'll just plot a monotonic line with the right slope and everything. So that's pretty straightforward as well. So please, use your sense of design to sort of, and creativity to choose the best way to present it to us. But yeah, there's many different approaches which I think will be acceptable. Yeah. Okay, well, we're at reached 7. If there are more questions, please contact us tomorrow during consultation hours. Remember, there's 2 hours, one between 5 and 6 with Yoni, and a second hour, I believe it's 7:30 to 8:30 with me tomorrow evening. Thank you.